Today we're going to talk about increasing, decreasing, and the first derivative test. So a couple definitions I got written up here for you already. A function is said to be increasing if on an interval, for any two numbers x1 and x2, in that interval where x1 is less than x2, then also the function value f of x1 is less than f of x2. All right, so graphically what that looks like, if you want to have visual interpretation, we have a set of axes here, and we have x1 is before x2, in other words x1 is less than x2, f of x1, and up here higher, right, f of x2. So this graph is increasing because x1 is less than x2 and it's increasing. That means it implies the y value at x1 is less than the y value at x2. Conversely, if we're looking at a decreasing function, and this is stuff you guys know already, just looking at it in a slightly different way. If x1 and x2, same situation, x1 is before x2. However, f of x1 is higher than f of x2. Now we have a decreasing function going through there. Okay, so it's a matter of going uphill versus going downhill. So real easy tests for testing for increasing and decreasing. So how to test for increasing / decreasing. Well, if you think about it, if we're going uphill, that means you have a positive what? You have a positive slope. If you're going downhill, you have a negative slope. And we know a lot of calculus deals with derivatives, and derivatives we know are slope. So as we start everything off, we're going to let f be a function that is continuous on the closed interval. So let's throw that in here. Let f be continuous on the closed interval from a to b and differentiable on the open interval from a to b. Okay, if that is true, we have three different scenarios that can occur. Scenario 1 states that if the derivative is greater than 0, for all x, right, for all x in the open interval, then we're increasing over the closed interval from a to b. Second scenario, if the derivative is less than 0 for all x in a, b, that implies we are decreasing over a, b. And the third one says that if the derivative is equal to 0 for all x, that implies we have a constant function. We have a horizontal line. It's constant over AB. All right, and I think those are relatively obvious here, right? If the derivative is positive, that means your slope is positive. If your slope is positive, you're going uphill. Uphill, we just saw meant you were going, you had the increasing scenario. x1 was less than x2, implied that f of x1 is less than f of x2. Okay, and the same is true for numbers 2 and numbers 3. So let's look at an example here, and then we'll move on to the first derivative test. So let's take f of x is some cubic function that we know has some twists and turns in it. X cubed minus 3/2 x squared. So my derivative is going to be 3x squared. Whoops, ignore that. I got a coverage coming up here. Let's dismiss. Let's see where we're at. 3x squared minus 3x. Now I want to see its relationship to 0, so I'm going to set this guy equal to 0. And I'm going to factor out a 3x and get x minus 1. So I get some critical values at 0 and 1. Okay? So I need to figure out what happens to the left of these critical, to the right of these critical, etc., etc. Notice there are no points in non-differentiability. I don't need to worry about anything like that. I just want to set up a table. I have an interval going from negative infinity to 0 another interval going from 0 to 1, and another interval going from 1 to infinity. Right, those are the three parts of my graph. And I don't need these parentheses over here. All right, so this is my interval. I need to figure out what my graph is doing over that interval. So let's pick a test value, a test number, something between negative infinity and 0. I'm going to pick negative 5. Okay? Negative 5, when I plug in negative 5 into my derivative, where we I get a negative times a negative, which is a positive. That gives me a positive derivative. Here, let's say I put in 1/2. If I put in a half, I get a positive times a negative, which is a negative. And here we'll put in 5. Positive times positive is positive. So this means, so the meaning or the conclusion, as the book calls it, I like to call it the meaning is that this is increasing, and then it's decreasing, and then it's increasing again. So graphically speaking, if I have room for my graph here, critical value at 0 and at 1. Okay? Critical values at 0 and at 1. And we can take this a step further. When I plug in 0, I get 0. When I plug in 1, I get 1 minus 3/2, which is what? Negative 1/2. So that's 1 comma negative 1/2. I know that my graph is increasing from here to here, the left side of the graph. And then I know it's decreasing from 0 to 1. But then I know it increases from 1 to infinity. So I know my graph goes like this. Increasing, increasing, increasing. Oh, now it's decreasing, decreasing, decreasing. Now it's increasing, increase. Okay, so I know my graph looks like that. Okay, and we can take it a step further and find some extra zeros of the function here, right? And decide when those guys are equal. Like that's at 1.5 there if you want to plug it in. But that's not really our concern right now. We're looking at the increasing, decreasing portions of the graph. Okay, so this was increasing, and then here it is decreasing, and then here it starts increasing again. Okay, over those sections here, and I can even, just to make sure we're all looking at the same stuff here, increasing, 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 increasing. This portion here is also increasing. And over here we are decreasing downhill. Okay, so that's our increasing, decreasing pieces right there. One last piece to talk about here is the first derivative test. The first derivative test. And the first derivative test simply states that if f of x goes from or changes from, goes from increasing to decreasing, right? We're going to go from increasing to decreasing, increasing, decreasing at x equals c. Then we have a relative, what do you think there? We have a relative, that's the top of there. We have a relative max at c comma f of c. Conversely, if f of x goes from decreasing to increasing, this was increasing to decreasing, so now we're decreasing, and then we're going to increase at x equals c. Then we have a relative min. Right? This was a relative max because it went up and down. This is going down and up at c comma f of c. And then, of course, if f of x does not change from increasing to decreasing, or whatever, does not change increasing, decreasing, then x equals c is neither a relative max nor a relative min. And that is your first derivative test there. One last piece there. I know I said the last one was the one last piece. Remember, another way to look at this goes from increasing to decreasing. In other words, f prime of x goes from positive to negative, right, when the derivative changes. So if we backtrack, let's look here, we notice that this graph, the derivative went from positive to negative, or the function went from increasing to decreasing. This is a relative max by the first derivative test. Right? I don't need to plug in that point anymore to determine which one's bigger and which one's smaller, because I see it goes from increasing to decreasing. And likewise, decreasing to increasing, or negative to positive, that means this is a relative min. And notice the change occurs at 1 and at 0. So that's your C value is 0, your C value is 1, so 1 comma negative 1/2 is your C comma f of C. Okay? And strictly monotonic is the last thing we are going to define. I mean it this time when I say last thing. Strictly monotonic. Okay, that is when a function f of x does not change from increasing to decreasing or vice versa. In other words, it's always increasing or always decreasing. Okay? Then it would be considered strictly monotonic. So for instance, this function right here, you can look at y equals x cubed. Okay, that is always increasing. Even when it changes its concavity, which we'll talk about later, this is still increasing. Strictly monotonic. Negative x cubed. Strictly monotonic. But let's take, so this is decreasing, decreasing. But let's take, for example, x to the 20th or something like that. Bad example, x to the 21, we'll have to do an odd one, where it starts to get a little flatter in here. Okay, yeah, this is increasing, and yeah, that is increasing. But over this stretch right here, that stretch right there is a constant. And x to the 21st is not a great example for that. That's not really constant there at all. You'd have to do more like a piecewise function where it's horizontal in there for a little bit. So let's put constant. So this would not be not monotonic. But these two are both strictly monotonic. All right, so that is increasing, decreasing, and the first derivative test. Hope you got a little bit out of that one. We'll see you later.